Now we look at how sound propagates in the medium from one region to the other region. The pictorial representation of a sound wave. That means how the sound is produced out of a tuning fork and how it travels in the waveform, and the compressions and rarefactions are compared to the waveform, the manner in which they can be compared. All these things we have to look at. For that sake, initially I'll just look at, there is a tuning fork which is undergoing a compression, which is undergoing a vibration. So whenever a tuning fork is vibrated, then I'm just considering one of its prongs. So prong is going away here and going inward here. So as I told you, whenever the prong is going away, then it will exert a pressure on the particles, medium particles nearer to that. Therefore, these particles come closer. So the particles come closer here and there exists a pressure on them. So they are compact here. Now when the tuning fork prong is coming back here, the prong is away from the mean position and here it is inward. In this case, these things are a little expanded. So here they are traveling in this manner. That means there will be a greater separation between the particles. So like this. Then again, after inward motion, then prong will be coming out. Prong will be coming out. Again, it is going to be a compression. So here they are getting narrowed here. That means they are compressed nearer. The particles are coming nearer. Later, the process continues because it is undergoing a to and fro motion. That is the reason. Next, in the next sense, it is again elaborated. So there is a fine gap between the particles. The pressure can be less. So this is what we are calling as the rarefaction. So this is how the compressions and rarefactions are produced. Here I am calling these as the compressions and these as the rarefactions. Compression, compression, and this is the rarefaction, and this is the other rarefaction. The same thing we can represent in the form of a wave. So the wave representation of the same phenomenon, the compressions, rarefactions are going to be like this. Here, if at all I represent the same motion, when the particles are compressed, the air particles are coming closer and at one stage they are, here the compression is going to be this, rarefaction is going to be this, again compression, again rarefaction. This is what we call as compression, rarefaction, compression, rarefaction. And the propagation of the wave is going to be from this end to this end. So this is what the propagation. This is called as the propagation. So wave is propagated in this manner in the form of compressions and rarefactions. So whenever the particles are closely oriented, then you call it as the compression. When the particles are farther apart, you call it as the rarefaction. And one compression plus one rarefaction gives rise to a complete wave. So you need to remember here, wave means one compression plus one rarefaction. So this is called as a wave. Now we look at the properties of this wave and terms associated with this. Here, this wave is corresponding to the compression. This wave is corresponding to the rarefaction. Again, this wave is corresponding to the compression. Likewise. So here, alternatively, the compressions and rarefactions will occur. Simple to note, whenever the tuning fork vibrates, the prongs are compressing the air particles, giving rise to the high pressure regions over there, which is called as the compression. And again, whenever the prong is going back, moving inward, then there will be a wide separation between the particles. That is what we are calling as a rarefaction, which takes place alternatively as long as the tuning fork is vibrating. So the sound so produced will be transmitted through this medium to the other end. And here you need to remember, it is making to and fro motion in the sense particles generally, if at all you consider the medium, the particles will be vibrating with respect to their mean position but not the actual movement. That is the reason in case of the sound wave, the particles are not actually moving without the actual movement. So in wave motion, the particle takes the energy, transfers to the next particle, then it comes back and take the energy from the previous one and takes it, transfers to the next particle. Likewise, energy will get transferred, but the particles mean positions will remain at the same point. So without the actual movement of particles, this mechanism is transferring the energy from one place to the other place. Here the sound is produced and it is getting transmitted to the other end without actual movement of the material particles. Now we are to look at the properties of this wave. So wave, and here we are looking at the terminology associated with wave. Terminology. So terminology of the waveform. So first of all, a complete wave. A complete wave means this is called as the complete wave, as I said. So I am just taking one complete wave here. So one point you need to remember, this is repeating at regular intervals of time. So one compression and one rarefaction. One compression and one rarefaction is going to be a complete wave. So upper side and lower side it will go with the same amplitudes in fact. So you need to write with the same amplitudes over here. So this is the complete wave. So amplitude over here, this is called as the amplitude. This is called as the amplitude. And here it is going to be at the negative side. So this is going to be minus A. So this is a complete wave. Now when a particle starts from here, if it undergoes one compression and rarefaction, after complete wave, the distance it travels is called as wavelength. Wavelength. Wavelength is nothing but distance travelled by a particle in one complete wave propagation. So distance between, you can define this as distance between two successive compressions or rarefactions. That is called as a wavelength. That is denoted by lambda. That means if at all you have a wave, if you have a wave like this, suppose a wave is moving like this, then distance between this point and this point, between two successive compressions or between two successive rarefactions, between these two also you can take, which is coming out to be the length of one complete wave, which is same as that of from here to here. This is also okay in calculating the wavelength. Wavelength can be calculated in any manner like this. So this is the first term associated with the wave, that is wavelength. Wavelength is nothing but distance between two successive compressions or rarefactions, or distance between two similar points. So this is called as a one complete wave. So this is how the wavelength can be calculated, and the units are going to be meters. But in case of the smaller waves, meter is a huge unit. Generally we measure in angstrom. So 1 angstrom is equal to 10 power minus 10 meters. So generally the wavelengths are measured in angstroms for the smaller waves. That means high frequency waves where the wavelength is very small. The smaller value of wave can be measured in terms of angstrom. 1 angstrom equal to 10 power minus 10 meters. This is the conversion factor. Meter is a big unit. Even you can measure the smaller wavelengths. That will be in the order of 10 power minus 10, which is called as the angstrom.